In this video, we're going to talk about standard conditions, standard states, and standard entropy. And first, we just start with the definition of what a standard state is. And it's just a certain set of conditions that chemists use so we can talk about reactions using the same criteria so we all know what we're talking about. For a gas, the standard state is if your gas is at 1 atmosphere. For a liquid or solid, it's your substance that's pure in its most stable form at 1 atmosphere pressure and some temperature of interest. So that's usually 25 Celsius, room temperature. For a solution, it's your substance in the solution that has a concentration of 1 molar. Now let's talk about the third law of thermodynamics, that is absolute entropy, and that is how much entropy or energy dispersion are there in a certain amount of particles. And to do this, we need a reference point, and so we use a reference point at 0 degrees Kelvin, or absolute zero. And we say that absolute zero, entropy is zero. There's only one state, there's no entropy, there's no movement, so entropy has a value of 0 at 0 degrees Kelvin. And so we say that that value is 0 joules per mole. Like I said, perfect crystal doesn't move, there's only one position. So when we talk about absolute entropies of anything else, that value is always going to be positive. The lowest you can go is 0. Everything above that, any temperature above that, will have some positive value of entropy or disorder. So let's talk about standard molar entropy then. It's given this unit S naught, this little circle here, that's what we call naught. And it's extensive. That means it depends on the amount of stuff we have, which makes sense. Look at the units of standard molar entropy. Joules per mole K. Mole is in the unit, so the more moles you have, the more entropy you have. And standard molar entropy values is for 1 mole of substance at 298 K or 25 C for a particular state or a particular allotrope, a particular molar complexity, molar mass, and degree of dissolution. What that means is we just define molar entropy for just about every state you can think of. So here we have oxygen gas, water gas, they are given entropy. Then you can go, well, we have water liquid, and there would also be a water solid. Here is just a very brief chart. But you can see that we have different molar entropies for different types of elements. And you will also find when you look at a table, you'll find like carbon in a diamond versus carbon in a graphite. Those are different complexities, different allotropes. Now let's look at these standard entropies and get some sense of the values associated with them. And our first comparison is gas to liquid. Gas has a higher standard entropy than liquid, which makes sense. Gas has more different states it can be in. It can spread its energy in different ways, therefore its entropy is bigger. And for standard entropies, as you get heavier, the bigger your molar mass, the more entropy you have, because you have different states you can put your electrons in. You have more electrons, you have more protons. Since you have more stuff, you have more ways you can distribute energy, you have bigger entropy. Also for allotropes, different allotropes have different standard entropies, and it really has to do with the constraint of your structure. Diamond is very constrained in compared to graphite. That is because diamond has extra bonds where graphite does not. These extra bonds mean that it has less movement. So diamond has lower entropy than graphite. And also, the more complex a molecule is, the higher entropy. So here, molar masses, argon versus NO. NO actually has a smaller molar mass, but there's a triple bond between the nitrogen and oxygen, which makes it more complex, which means we have higher entropy. And here we have carbon monoxide versus C2H4. These have the same molar masses, but C2H4 has more bonds, so it has higher entropy. And when you're comparing something that's solid or something that is dissolved will have a much bigger entropy because it is now has more movements. It can interact with more things. In the solid form, it's kind of stuck. And when we're talking about entropies, we can have delta S. That is, in a reaction, how does our entropy change? And we say delta S, not reaction. That is, the change in standard entropy for our reaction is the sum of the number of moles of each product and the standard entropy of those products, all added together. That's what that sigma means, minus the number of moles of our reactants multiplied by the standard entropy of our reactants, and you add up all the values for each reactant. And remember, you should always get a positive number for our standard entropies. The lowest entropy you can be is 0, and so you should be above 0. So at 25C, if we want to see if something is spontaneous or not, so this is a throwback to a previous video, we say the change in our Gibbs free energy is our products minus reactants. Well, at other temperatures, we can find this out if we know our standard enthalpy of formation and our standard entropy. So delta G equals delta H minus T delta S, which is the reaction we talked about. So now we've talked about, throughout chemistry, all the different ways we can measure delta G, which is very important because, again, it is telling us whether a reaction will be spontaneous or not under certain conditions. That's it for this video. I will see you in the next video.